name is Javier Prado. I am a secondary school teacher, but I have made my PhD in science teaching with a doctoral thesis about the way to teach relativity in younger ages with the help of the Minkowski geometry of space-time. It sounds very complicated, but I will try to show that this is not so complicated, and the advantage will be that maybe you can see with your eyes why the relativity effects are so and why there are deep reasons that they are so. Well, as I told you, relativity, as established by Minkowski, Hermann Minkowski was the mathematics teacher of Albert Einstein, and he showed that relativity, all the relativity, special relativity theory, is geometry in a very complicated kind of geometry, tensorial geometry in 4 dimensions that usually people don't want to understand, but I will try to show you how this can be viewed directly by your eyes. The way we do that is to change the normal reality that we have in front of us, 3 dimensions. I show you here the usual way to see 3 dimensions. And please take in mind that this is not 3 dimensions. This is a flat surface, but our mind has the ability to show 3 dimensions in only 2, using perspective and some strategies. But our mind is not able to see 4 dimensions. We are not so developed. Maybe future species can do that. We cannot do that. So we must apply to a kind of simplification. This simplification is, we forget the 3 spatial dimensions that we see, and we remain only with 1 spatial dimension. We replace it horizontally. And the advantage is that we can now place time, which is normally represented by a clock, in this geometric representation is vertical. We make also a kind of space-time unit cell, like in crystallography. The unit cell, its geometry explains the geometry of the great crystals. Also the unit cell of space-time will explain the geometry of the whole space-time. This unit cell, every one of you can make it with me if he or she wants. With the arm placed horizontally, this is approximately 30 centimeters, and the time the light needs to travel 30 centimeters is 1 nanosecond. So if I make that this vertical line represents 1 nanosecond, we have a unit cell of space-time. The main fact of this unit cell is that now we have a square, and like this, the diagonal of this square. This fact is very important, and we will recover it at the end. So now we have space-time. We go back in time to the old time of Greek philosophy and science, to the figure of Aristotle, the great philosopher and the first scientist, the one who created the world, physics. And he told us that reality is made by space, time, and movement. We put both together, and we have here represented these ideas from Aristotle in space-time. You see a particle or a body at rest would trace a vertical line in space-time because it would not change its place as time passes. But if the line is inclined, it will have a movement. If the inclination is greater, the movement will be faster. And there is no, in principle, no problem, no obstacle that if we have speed of light, diagonal, you have seen it, that a particle can travel faster than light. I see no problem in doing that, in accelerating greater than light. But Aristotle told us that there is a limit. A particle, an object, can never reach the instant. He defined the instant as the separation between past, which is not real because it has already gone, and future, which is also not real because it has not gone. The reality is the instant. My instant now is a horizontal line, but your instant is all what you see. Yes? You understand this simplification. So, a particle accelerating can never reach the instant. And this has already explained Aristotle, because in this case, this particle would be in all places at the same time. And a real particle cannot do that. Only maybe God, but we are not speaking about that. Yes? So, there is a real limit. But the speed limit is not the speed of light, it is, in this case, infinite speed, which is much greater than the speed of light. We will come to this limit, but not now. Yes? So, with my students, I make
some sentences to recover all these ideas, but I will not make that. We have played with these sentences yesterday, so experimental evidence that we will not put here has shown that the way the unit cell of space-time changes is like is shown here, like the Lorentz transformation. This is the visual representation of the Lorentz transformation. The unit square of space-time stretches in one diagonal and gets shortened in the other, but the speed of light, you see the diagonals does not change. The inclination of the diagonal does not change. What is the great change in this figure? That the instant, Aristotle's instant, the only real existence, is now inclined. It is now inclined. And this will have deep meaning and it will follow us until the end of this exhibition. Yes? We will use only this property of the instant, of its inclination, to show how we can understand the main relativity effects. And we will at the end see also some experimental evidence, not the one who has led to this Lorentz transformation, but a kind of experimental evidence of all what I am presenting you. But just wait until that. What we will explain using this figure is how there is a limit, a speed limit.
Remember that the movement could not reach the instant. This was an unattainable limit. But if now the instant rises when the movement is accelerating, then the limit is when the movement touches its own instant, and this happens at the speed of light for an external observer.
So the limit already established by Aristotle now comes to the encounter of the movement, and it is impossible that the movement can surpass the speed of light because it would touch its instant. And a lot of scientists are wasting time and money trying to find particles that can go faster than light. The last experiment was the neutrino opera experiment, and if they had this idea in mind, only thinking about what Aristotle had very clearly, they would not make these kind of errors. I hope this does not happen also in the future. So, now we can go into another relativity effect, which is the equivalence between mass and energy, established by Einstein with his famous formula. For some people, the most famous formula in physics, E equal mc squared. And we will show how to understand this formula. Well, first of all, we will make a space-time lever. We have shown also yesterday how to build levers. I will not repeat that for you. But only think that in particles collisions, two particles come one against the other at the same speed, and if they remain at rest, what does this mean about their masses? Whose mass is greater if they remain at rest at the same speed? They have the same mass. You can see that. But if the mass, in this case, the mass of the right is greater than this other mass, and they come at the same speed, what happens is that the greater mass drags the smaller mass. And if we go back with the center of mass in time to reach the instant, as it is here, you will see that now the instant, the famous instant, helps us to build an imaginary level in space-time where the fulcrum, that is the center of mass, is dragged by the greater mass in the same way as any lever operates. Yes? So, what does this mean? I will show you a figure. You may build it by yourself, but please believe me that if you make this space-time graph of a collision, the instance, this is a particle A and this is a particle B, the instant of A, IA, becomes perpendicular straight onto this other side, and the same happens to this other instant. They fall straight on the other side. Yes, this is the particle A coming to the right, and particle B coming to the left. Stressing the symmetry of this figure, we will work with an equilateral triangle, the most simple case of triangle. The speeds of these masses must be approximately 2/3 of the speed of light, 200,000 kilometers per second. But accelerators can go much faster. So, what happens in this figure? This is particle A, this is particle B, this is the at rest center of masses, and this is the instant of A, and this is the instant of B. Equilateral triangles have the property that this part of this side is 2 times greater than this other one. So, and now to bring energy into these diagrams, we will use the pendulum.
A very old artifact also used by classic physicists like Newton, A pendulum is a device that transforms energy into different forms, potential energy into kinetic energy, keeping all the time its value. Yes?
What happens with a pendulum? Thank you very much, Sander, for your pendulum. If we use a pendulum with a special dimension that it is explained in our paper, you have it in the book, you can read all the measurements to be made there. A pendulum,
its length is made equal to its mass, then the separation from the vertical, from the at rest position, will be the speed at which it arrives here, and its height, if this is the horizontal line, its height with respect to the horizontal will be its energy.
The energy is the height. You see it here in red. This is the main fact that I will try to show you with the pendulum, that the energy is the height of it. But if we make that this pendulum comes into space-time, now we have no horizontal line. Or do we have our horizontal line? The famous instant, yes? Only 3 minutes. Well, I must be faster then. The horizontal limit is the instant, and so the energy is the distance to the instant. So, Archimedes, another great scientist of all times, has shown us that it is possible to explain the law of the lever with a figure such as that. Do you see it here? 3 equal masses must have their central point in the middle.
If we make such a construction, you can see and understand that now, if we have a double mass, its distance is the half of this one, so that distances and masses are inversely equivalent. Yes?
And if we go with this figure to the previous construction, now we see that we have a mass, and on the other side the mass and its energy, which goes to the instant. And this distance, the instant, is double to this one. So this set must be double of this one. So energy must be equal to mass. But you may say, and where is c squared? The Einstein formula is not only that. But remember, c was equal to 1. C squared is equal to 1, and now the famous Einstein formula, I apologize with my students always because it loses its magic. It is no more magic. C squared is not important here. The only important thing is that E is equal to M. And this has important effects because energy can be transformed into mass, as we have seen, but in the CERN, it is not only one particle. There are more than 2,000 particles arriving from one mass.
And also at the Sun, this is the International Year of Light, 2 hydrogen atoms can join together to produce a helium atom that is a small lighter than them, and the energy escapes in the form of light that arrives us.
And finally, very fast, we can also see electricity as 2 kinds of different opposite particles, positive and negative, coming against one of the other. And you see here negative particles to the right, positive particles to the left, and the instant of the negative particles sees that now the distances between the negative particles are greater, you see here, and the positive particles are contracted. If you move with a negative particle, you will see more positive particles, you will be attracted. And this is explained usually with magnetism. We don't need magnetism if we have relativity. This is the famous Ampere law between attraction and electrical currents. If they are perfect, we have a solenoid and also a magnet, and motors can be explained with that. And also, if we think in this room as a great magnet where currents flow around it.
If I move a conductor rod and I force it to go in this direction, the particles in this rod follow the direction of the current, so they will be attracted and repelled. There is an electric current inside of here. And if I attach a lamp into it, when I move it, it will light. This is the experimental evidence I told you. You may say, but there is no light. We must believe you. But we have no magnet here around us. In this small device, you can find it in every Chinese shop. We have a magnet, we have a rod, and we can force the rod to move into the magnet. And I hope light will appear.
So, this was all.